Okay, welcome to robotics. In today's class, we are officially starting the next chapter, which is dynamic analysis and forces. So, dynamic analysis of robots. Now, what does this topic talk about? It talks about a robot, and let me give you a very simple example. Imagine that you have, say, a two-axis or 2 degree of freedom robot. So two links, L1, L2. Each link has mass M1, M2. And now you have an end effector, say a gripper at the end. So when this robot is going from point A to point B, we are interested in finding out not only the values of theta 1 at that instant, but we want to find out the evolution of theta. So how theta changes. So essentially, I am interested in the dynamic analysis wherein I will have equations of motion. So I will have differential equations of motion. So what does a differential equation of motion for robot mean? Differential equation of motion for a robot tells us how the robot evaluates. How the robot changes its positions and velocities. So I'm interested, if I have a variable theta 1, I'm interested in time evolution of theta 1 with respect to time. Then I'm interested in finding out value of theta 2 with respect to time. That looks like this. I'm interested in finding out the velocities, which is theta 1 dot with respect to time. So you can have velocity like this. And I'm interested in finding the velocity theta 2 dot versus time. Now, please note, these parameters are dependent on forces, moments, and the inertia properties. So the first and foremost, what do I mean by differential equation of motion? And all of you must have taken differential equation class, but I just want to give you a quick 1 minute overview. Look at Newton's law. Force is equal to mass times acceleration. Now, in this equation, force is a vector. That's why indicated by an arrow on top. Mass is scalar and acceleration is also a vector. If x is the displacement, dx by dt, which is the first derivative with respect to time, is velocity, and d by dt of dx by dt is d2x by dt square, which is x double dot, is acceleration. Now, if I were to write this equation something like this, say f is a function of time is equal to mass times x double dot, this is nothing but a differential equation. And what I need to do is I need to integrate 2 times. So we need to integrate twice to find the relationship between x, which is the dependent variable, and time. Now, please understand, what does it mean that to find the solution? So in other words, I need to find out x, I need to find out x dot, I need to find out x double dot in such a way that when I substitute the equation for x double dot, which is equation 3, in equation 1 gets satisfied. So what it means, the solution of the differential equation, the solution of differential equation is a function that satisfies the differential equation. Now, how do we find out this solution? If you have taken differential equation class, then you probably know a lot of techniques, analytical techniques to find the solution of differential equation. But many a times, the differential equations that we see in robotics, or for that matter in usual uh, physical systems, they are very complex. So when the differential equations are complex, we try to solve them numerically. Say one way to solve it is using MATLAB, and probably you have seen ODE 45, ODE 23. These are different routines that can be used to solve differential equations. So in next few lessons, what we are going to do is, we are going to look at a very standard technique to derive the differential equations of motion for complicated robotic systems. And please understand that deriving differential equations is not a trivial task. So manually, we can derive the differential equation for some simple systems. But once we understand the process, what we are going to do is we are going to use MATLAB that would automate the procedure for us. Now, what I want to show here is I want to give you a very simple example. Consider that you have a spring mass system. And this example is usually always discussed when we look at differential equation. So you have spring has stiffness K, and you have mass, which is M. So K is spring stiffness. And spring stiffness, by definition, is load divided by deflection. So what it means is, if you have a spring, you add the load, and that spring is stretched. So if you were to plot load versus deflection diagram, excuse me. So this is load, this is deflection. The slope of this straight line, slope is nothing but K. So the slope of this straight line is nothing but K. The unit is Newton per meter, where Newton is the unit of force and meter is the unit of displacement or deflection. Then you have mass. I'm going to derive the differential equations of motion using two techniques. So just let's look at this thought exercise. Imagine if I pull this mass and let it go. If I pull this mass towards right hand side and if I let it go, do you agree with me that this mass is gonna exhibit oscillatory motion? Now this motion is periodic, and the period depends upon the stiffness properties and the mass properties. So what I'm going to do is, first I'm going to use the known Newton's approach. So let me discuss Newton's approach. And this approach is something that you should be familiar with so far. I'm gonna draw the free body diagram for this mass. Before I do that, I need to assign the coordinate system. Please note, coordinate system is very important when you solve robotics problems. So since this is a planar problem, I have i's and j's, x and y. If my force, acceleration, displacement is towards the positive x-axis, it's gonna be positive. So any vector, if the vector direction is aligned with x direction. So please note, if vector, it could be force, it could be displacement, it could be acceleration, is in direction of positive x, it is positive. And please remember this, because we will, when we show the free body diagram, this convention will be used. Now let's assume that this mass is pulled towards right. So the mass is pulled towards right. So clearly, when the mass is pulled towards right, you're gonna have the spring force, which is going in opposite direction. So this is the force on the mass, and this is the force on the spring. So you have K times X. See, if this is the force, F, if this is the displacement, X, the spring force is K times X. And the acceleration, I'm going to say acceleration is in this direction, X double dot, and it has mass M. So now we have to derive the differential equations of motion using Newton's law. So I have force is equal to mass times acceleration. Now please note, force is kx. Kx is in the opposite direction of positive x. So kx is going towards left, but positive x is going towards right. So what I have is minus kx. And then I have mass. Mass is a scalar quantity, so it doesn't matter. And A, the acceleration is towards the positive right hand side, which is in the same direction as x shown in the figure. So the differential equation that I have is mx double dot plus kx is equal to 0. Now what I want to do is, I want to present an alternate approach, which is called as the Lagrange approach. Lagrange approach. And the power of this approach is, you don't need to draw free body diagrams. You don't have to derive the forces or find out the directions. So please pay attention. In Lagrange approach, there are only two things you have to find out. The first thing is kinetic energy, which is called as T, and then potential energy, which is called as V. And then there is a famous Lagrange equation that you use that gives you the differential equation directly. So you can derive the differential equations without drawing any free body diagrams. And the beauty of this technique is, this technique can be programmed in MATLAB. So what you need to do, I will give you the script. So this approach can be completely automated. So let's look at this simple example. We have mass m. The velocity of the mass is x dot. So the velocity is x dot. So the kinetic energy of the mass is going to be 1 half mx dot square. Please note, kinetic energy or energy for that matter is a scalar quantity. So kinetic energy is a scalar quantity. So it is just 1 half mx dot square. Now I want to find out the potential energy. What is potential energy? Potential energy is nothing but area under this straight line. And the area under the straight line is nothing but 1 half k x times x, which is 1 half k x square. So 1 half k x square is the potential energy, which is 1 half k x square. So now I have found out kinetic energy and potential energy. I just want to stop here for a second and ask anyone if anyone has any question. Everyone understood how I got kinetic energy and potential energy for this simple spring mass system? Because here is what we are going to do. When we are going to derive the differential equations of motion for any robot, we have to find out the potential energies for the robot. We have to find out kinetic energies for the robot, and then we have to go forward. So kinetic energy is 1 half mx dot square. Potential energy is 1 half kx square. Now here comes the equation. I'm going to define something called as L. L is called as Lagrangian. And that is the difference between kinetic energy minus potential energy. So L is the difference between the kinetic energy and potential energy, which is 1 half mx dot square minus 1 half kx square. And once you find the Lagrangian, so for every robot that we are going to solve, we are going to find Lagrangian. So there is something called as the Lagrange equation, and that equation is something like this: 0 is equal to d by dt, partial L by partial x dot minus partial L by partial x. And believe it or not, this simple expression, which is d by dt of partial L by partial x dot minus partial L by partial x, that gives you the Lagrange, the dynamical equation of motion. So let's try to find out what these quantities are. So everyone knows my Lagrangian is given in equation 2. This is my equation 2. This is the Lagrangian. So let's first find out what is partial L by partial x dot. Please note, we are finding out partial derivative. What it means is when we do this, x is equal to constant. So when x is equal to constant, please note my equation becomes 1 half m 2x dot, which is nothing but mx dot. The next thing is partial L by partial x, and this is again a partial derivative, which means x dot is equal to constant. And when I do the partial x, please note x dot is constant. So this equation becomes minus 1 half k times 2x. So this equation becomes minus kx. And now what I need to do is I need to substitute these two values in this equation. D by dt partial L by partial x dot is mx dot minus partial L by partial x is minus k times x. Please note, this is full derivative d by dt of mx dot M is a constant, so that comes out of the equation, and I am left with an equation mx double dot plus kx is equal to 0. So please note, we derived the exact same equation which is on the left hand side using Newton's approach, and we used a Lagrangian approach to solve the exact same problem. And the next part is, how do we solve this differential equation? And we will look at that problem a little bit later. In most of the cases, we'll solve these equations numerically. So we will use MATLAB, and then we will use the MATLAB solvers to solve this problem. And we can use Simulink as well. Before I proceed further, any questions? Okay, let me take few more problems. The second problem that I'm going to work out is sort of a robot arm, inverted robot arm. But in this robot arm, the mass is concentrated at the end. This looks like a pendulum. So what we have here is, this is M, this is mass of the pendulum, this is length of the pendulum, which is L. This angle is theta, and I'm going to assume again the same coordinate system. Please note, I have X, Y, and Z. This is X, Y, and Z is coming out. So this is the coordinate system that I'm using. So what I want to do is, first and foremost, I want to solve this problem using Newton's technique. So please note, this is mass. So the force because of the gravity is m times g, that is going down. And when, let's assume that I am adding counterclockwise motion. So my theta is counterclockwise, my theta dot is counterclockwise, my theta double dot is also counterclockwise. So the Newton's law, which is given as force is equal to mass times acceleration, when we apply to the torsional systems, this force gets converted to torque. You have torque is equal to m, which is the mass. Now you have the mass moment of inertia, and instead of a, you have alpha, wherein I will write what they are. So you have t, which is torque. Then you have alpha, which is angular acceleration. And then you have I, which is mass moment of inertia. And just to give you what is the definition of mass moment of inertia, mass moment of inertia is mass times the radius of gyration square. So radius of gyration is nothing but the distance between the CG of the mass and the point about which the mass is gyrating. So just to give you an idea, if you have a mass m, and this mass m is rotating about this point, and this length is r. So if this radius is r, the radius of gyration multiplied by square multiplied by mass becomes m r square. So the radius of gyration is m r square. So now the Newton's law in torsional coordinates is expressed as t is equal to I alpha. So let's apply the same technique. Look at the external torque that is acting on this system. External torque acting on the system is m times g multiplied by this torque arm, which is L sine theta. And this torque is in the clockwise direction. So if you look at the way this torque is like in this direction. This is the direction of torque. So this torque, when you curl your fingers in the direction of the torque, your thumb is going inside the board, which means this torque is negative. So you're going to have minus mg sine theta as the torque. Then you're going to have I. And please note, uh, alpha is nothing but theta double dot, which is the acceleration, angular acceleration. But angular acceleration is positive. If you curl your fingers in the direction of angular acceleration, your angular acceleration is positive. So you have theta double dot. So in other words, if I were to write this equation, I get I theta double dot plus mg sine theta is equal to 0. Now I is the mass moment of inertia, and mass moment of inertia is nothing but ml square theta double dot plus mg sine theta is equal to 0. And here m gets cancelled, and I missed one L. So there is an L here, mgl sine theta, mgl sine theta, mgl sine theta. So this equation becomes theta double dot plus g over L sine theta is equal to 0. Yeah, so I think my equation is correct now. So I have theta double dot plus g over L sine theta is equal to 0. Now what I'm going to do is I'm going to try to solve the same problem using Lagrange approach. So the only thing that you need in the Lagrange approach is the potential energy and kinetic energy. So for the pendulum problem, the kinetic energy, let's start with the kinetic energy. Kinetic energy is equal to 1/2, then you have mass m and the velocity of the mass. So think about it, this velocity of the mass, this is v, which is r theta dot. And remember this equation that we studied in mechanics, velocity is equal to omega times r. Omega is theta dot, r is L. So you have theta dot L. So kinetic energy is 1/2 mv square. So I have theta L square. So which is 1/2 m L square theta dot square. This is the kinetic energy. And then I'm interested in potential energy. So potential energy is V. And let's find out what the potential energy is. Potential energy depends upon datum. So for an example, what I'm going to do is I'm going to consider this pendulum mass over here, and I'm going to treat this as my datum. So this is my datum. So I'm interested in finding out the vertical distance between the datum and the position of the mass. This is L, this is theta. So this distance is L cosine of theta. So my potential energy is nothing but, since the mass is below the datum, please note mass is below the datum, my potential energy is minus mgl cosine of theta. So my potential energy is mgl cosine theta. Now, any questions in finding out the kinetic energy and potential energy? Okay, since we don't have any questions, I am going to solve uh, for Lagrangian. Lagrangian is, this is T, this is V. Lagrangian is T minus V, which is kinetic energy minus potential energy. So this becomes 1/2 m L square theta dot square minus minus plus, which is mgl cosine of theta. So now this is my Lagrangian. And once I have the Lagrangian, I have to apply the Lagrangian equation of motion. And this may seem like a little bit tedious thing at this first problem, but please note, the good news here is you don't have to look at the forces, or you don't have to consider free body diagrams. Once you find out the kinetic energy, once you find the potential energy, boom, you can program, you can have a program written in symbolic toolbox in MATLAB, and that would actually compute all the solutions for you. So the equation is d by dt. Please note, this is full derivative, partial L. And in this case, I have theta and theta dot. So I'm going to have partial L by partial theta dot minus partial L by partial theta. And with this, I'm going to work out these values on the side. So partial L by partial theta dot means theta is equal to constant. So this equation is going to be m L square theta dot. So I have ml square theta dot as partial L by partial theta. Let's do partial L by partial theta. In this case, theta dot is equal to constant, and my equation is going to become mg comes out as constant, mgl comes out as constant. Please note, I have a cosine theta. Derivative of cosine theta is minus sine theta. So I have this equation, and I'm going to substitute these values over here. D by dt partial L by partial theta is ml square theta dot minus mg L sine theta. Let's not forget that there is a negative sign here. So this equation now becomes m L square theta double dot plus mgl sine theta is equal to 0. So m cancels out, L goes, L square goes, and finally you have the equation theta double dot divided by g by L theta, g by L sine theta is equal to 0. So we derived the exact same equation using both these approaches. Any questions here? Any questions here? Okay. Now what I want to do is, I want to talk about something which is called, what do I mean by solution of the differential equation? And this stuff is super important. So super important material. Now, as we discussed earlier, what do we mean by solution of differential equation? Solution of differential equation is a function of time that satisfies differential equation. Now the question is, how do you find this solution of this differential equation? And I'm going to talk about a very simple approach. The derivatives, yes. So if you have x, which is displacement, x dot is equal to d by dt of x, which is velocity, and x double dot, which is d2x by dt square, which is acceleration. So let me work out what I mean by this problem, and then will try to answer that question in just a second. So I want you to remember only one thing. Most of the differential equations that we can solve by hand are linear differential equations. Differential equations. And for linear differential equation, I'm always going to assume the solution as a e to the lambda t, where a is a constant, lambda is a constant, and t is equal to time. And why am I using an exponential function? And the reason I'm using exponential function is when I take the derivative, so if I do x dot of t, this derivative becomes a times lambda e to the lambda t, which means the function gets repeated. Then x double dot of t becomes a lambda square e to the lambda t. Now, something interesting about lambda. Lambda is multiplying time. So I want you to note something like this. I'm going to plot on this plot time and e to the lambda t. So on y-axis, I'm going to show e to the lambda t, and time is t. So let's consider when lambda is equal to 0. When lambda is equal to 0, lambda times t is 0, e to the 0 is 1. So when lambda is equal to 0, I'm going to get a straight line. Everyone agrees with me? When lambda is equal to 0, I'm going to get a straight line. Now, please note, when lambda is negative, I'm going to have an exponential decay. If lambda is positive, I'm going to have an exponential increase. So what I'm going to do is, I'm going to show this is the case when lambda is greater than 0. When lambda is greater than 0, I'm going to have an exponential increase. And when lambda is less than 0, I'm going to have an exponential decay. So please note, depending upon the values of lambda, the x would change. So if I have x is equal to e to the lambda t, if value of lambda is positive, then it will become bigger as the time goes on. If value of lambda is negative, it will become smaller as the time goes on. Now I'm going to try to solve an equation which is the same equation that we talked about. So our equation that we derived was mx double dot plus kx is equal to 0. So mx double dot plus kx is equal to 0. This is the differential equation. And I want to solve this differential equation. And I'm going to start with the assumption my x is equal to a multiplied by e to the lambda t. So my equation looks like a e to the lambda t. Then my x double dot is going to look like a lambda square e to the lambda t. So what I have here is the equations that I have on the right hand side, equation 1 and equation 2. I'm substituting equation 1 and 2, substituting 1 and 2 in 3. So I substitute equation 1 and 2 in equation 3, and I have this equation. Please note, lot of terms get cancelled. A gets cancelled, A gets cancelled, e to the lambda t gets cancelled, e to the lambda t gets cancelled, and the equation that I'm left with is m lambda square plus k is equal to 0. Now what this means is, please note, value of m is a physical quantity, which is, for an example, mass. Mass is given in kilograms. So it could be 2 kilograms, 3 kilograms, 5 kilograms, 10 kilograms. Value of K is a stiffness constant that could be 5 Newton per meter, 10 Newton per meter. It's a number. But if I give you the value of M and if I give you value of K, please note, you can tell me the value of lambda. So lambda square is equal to minus K by M. In other words, lambda is equal to plus minus square root of K by M I. So my lambda is plus minus square root of K divided by I. And believe it or not, this is the solution of the differential equation. So my solution of the differential equation is going to be x of t is equal to, there are two possible lambdas. So you have lambda 1, which is plus square root of k by m I, and you have lambda 2, which is minus square root of k over m I. And your x of t, since you have two lambdas, you are going to have two different a's. So you will have a1 e to the lambda 1 t plus a2 e to the lambda 2 t. And what is a1 and a2? Recognize it's a differential equation with two derivatives. It's a second order differential equation. So let me write this down. This is second order, which means two derivatives. So to find the solution of this second order equation, we have to integrate two times. So when we integrate once, we get one constant of integration. When we integrate one more time, we get the second constant of integration. So a1 and a2 are constants of integration. So constant of integrations are dependent on initial condition. So they are dependent on initial conditions. So what you will do is you will substitute at time t is equal to 0 the value of initial position and value of initial velocity, and that should get you the values of the initial term. Okay, so this a1 e to the lambda 1 t plus a2 e to the lambda 2 t is the solution of differential equation. This is nothing but the solution of differential equation. Now, one thing that I want you to understand, that for in this particular problem, please note I have purely imaginary roots. These are also called as roots. So roots. They are also called as eigenvalues. They are also called as natural frequency. So please note, these are purely imaginary, which means you have I. And whenever you have e to the, say, e to the omega I, from Euler's identity, what you have is you have cosine. So let me write this down. Cosine omega I, cosine omega plus I sine omega. So e to the omega I, where I is an imaginary number, I is square root of -1. I need to just write this down, square root of -1. This is a trigonometric or periodic function. What that tells me is if I were to plot x of t, if I were to plot x versus time, I'm gonna get a sinusoidal curve. This is how the solution of the differential equation is gonna look like. And I want you to do this thought exercise for a minute. Imagine that we have the same spring mass system. I pull the mass and let it go. I pull the mass towards right or push the mass towards left and let it go. The mass is going to oscillate back and forth, back and forth, back and forth. And that is going to be a sinusoidal motion. If there is no resistance, if there is no air resistance, or if there is no damping, those oscillations will continue for an infinite period of time. And that is what this solution of differential equation means. So once I know how that system is going to evolve, how is that x going to change with respect to time, I can find out the position of the mass or the velocity of the mass or the acceleration of the mass at any time I want. Okay. And I just, for the sake of completion, let me tell you when lambda or eigenvalues are greater than 0, and I need to write this down here. So lambda is called roots, also called as eigenvalues, also called as natural frequency. So, and I need to show you this plot here. This is lambda is equal to 0. And this, when lambda is equal to 0, the system is called simply stable. And let me give you an example of a simply stable system. So you have a ball on the flat horizontal surface. If you give it a push, what will happen is the ball will stay on the horizontal surface, but it would settle down at a different position. So a disturbance does not cause a major change. No major change. Now let's look at the other case when lambda is less than 0. In that case, the system is called asymptotically stable. And I want you to remember this example. It is like you have a bowl and the ball is inside the bowl. And now if you disturb it, what's going to happen is the ball may go on the right hand side, it will come back to the left hand side, go back to the right hand side, but at the end it's going to settle down where it was. So it will settle down at its original position. So disturbance, so no change, which means it comes back to its original position. And now you have lambda, which is greater than 0. This system is called unstable. So, and I just want to give you an example of an unstable system. So consider that you have a ball on the bowl on the opposite side. So for an example, if you displace the ball, then the ball goes, it never comes back. Ball never comes back. So disturbance, and this is unstable. So what I want you to understand is eigenvalues are super important. Eigenvalues are super important. They tell you whether the system is stable, asymptotically stable, or unstable. So now let me give you an example of a simply stable system. A simply stable system is a spring mass damper system, wherein it's going to show you a nice oscillatory response all the time. So you have mass and you have stiffness. This is a simply stable system. Asymptotically stable system is you have spring, you have mass, and you have a damper. So you have K, you have C, and you have M. And what's going to happen is, since the system is asymptotically stable, the oscillations will decrease and then die down over a period of time. Now, what means when the system is unstable? The system is unstable. Think about, I just want to give an example. Look it up. Tacoma, narrow, bridge, failure. And you can look at YouTube, wherein what happens is it's a spring, damper, and mass system, but it has flow induced vibrations. So you have spring and you have damper, but this damper is negative. So what happens is the oscillations kind of keep on growing until that bridge failed. So you have simply stable system. When oscillations are controlled, they don't grow, they stay within the bounds. You have a system which is asymptotically stable, wherein the oscillations die down, and you have unstable system wherein the oscillations continue to grow. Okay, uh, everyone understood what we did here? Any question? Actually, I want to work out a few more problems, but before that, let me work out or give you hints on the problem similar to the quiz problem. So, and I'm going to show you the technique that I discovered. It's you can use different techniques. At the end, your answers should be the same. So let me take an example that you have a robot arm, wherein you have a revolute joint, and then what you have is you have another revolute joint which is, say, at an angle. So I'm going to show another revolute joint, and this revolute joint is at an angle. and then you have an end effector over here. Please note it's constant. So this theta is say 30 degrees. And this is not changing. So no matter what happens, this theta is going to remain 30 degrees. Now, the question is, how do we solve this type of problem? Now, let's start with the coordinate system first. So first we have to assign the coordinate system. So I'm going to say this is going to be my z naught. This is going to be my x naught. And this is going to be my y naught. The next thing, which is logical thing to do, is assign the coordinate system for this joint. So I have z1, and then what I need to do is, all of a sudden, as soon as you come to z1, one question that pops up in mind is, hey, look, z1 is not perpendicular to z2. Z1 is not perpendicular to z2. So how do we assign values of x? Understand the condition for x1 is x1 has to be perpendicular to z1 and x1 has to be perpendicular to z0. So what I could potentially do is I could add my x1 something like this. I could add my x1 something like this. And then I could add a y1. So let's look at, I have x1, I have x1, I have z1, and now I have y1. And then what I'm going to do is I'm going to continue with the same approach. I'm going to say this is my x2, this is my y2, and this is my z2. Now, at this point, before we proceed any further, I need to take a step back and make sure that all my 4 rules are satisfied. First and foremost, z1 and z0, they are going through the joint. That's great. x0 is perpendicular to z0. Now, let's look at x1. Now, x1 is perpendicular to z1. x1 is perpendicular to z1. x1, if you were to translate, you would see that x1 is perpendicular to z0 as well, but x1 does not intersect. So I need to write this down. So note, x1 is perpendicular to z1, x1 is perpendicular to z0, but x1 does not intersect z0. And the most logical thing here, if you want to do it, is to translate x1. So if I want to translate, then I'm going to have x1, I'm going to have y1, and I'm going to have c1 like this. Now, as soon as I set up the problem this way, the problem seems to be solved, but recognize my projection matrix. And here is the issue that you want to be super careful about. Please note, projection matrices are not perpendicular, because when you start taking projections, say let me give you a simple example. Say you first find out 0r1. So you found out 0r1. that needs to be multiplied with a projection matrix. So I will write this down. 0 R1 is equal to, let me take an example here. If this is theta 1, this will become cosine theta 1 minus sine theta 1, sine theta 1, cosine theta 1, 0, 0, 0, 0, 1. Now I have a projection matrix, and that projection matrix would be x1, y1, z1, x0, y0, z0. Now, when we are trying to do this, x1, y1, z1, please note that there is this 30-degree angle that is floating around. This 30-degree angle that is floating around. And that would become part of this projection matrix. So, which means theta will be in projection matrix. And that could be a little confusing for some students, or it may not be as straightforward as we worked out before. So if you want to work out the projections of theta along x1 projection with x naught, so if you look it up, you will realize that uh, x1, which is over here, is actually at an angle 30 degrees because z1 is parallel. So you have rotations appearing in essentially x and z's. So you need to take those into account. Now, let me suggest the technique that I discovered. Okay, so I will try to work out the same problem, but now I will use the technique which is slightly different. That makes the problem lengthy, but then the problem can be easily solved with the approach that I have. So let me start the first kinematic diagram. And say this is angle, which is theta. This is a revolute joint. This is a revolute joint. Okay, before I proceed further, I just want you to understand, everyone understood this kinematic diagram and the issues that you potentially face because of the links are not perpendicular to each other. Now, what I'm going to do is I'm going to make a slight change to this kinematic diagram. So what I'm going to do is I'm going to add a virtual joint. This is called as the virtual joint. And this technique is not discussed in any of the books. So I'm going to call this a virtual revolute joint. So VR. And what is the purpose of this virtual revolute joint? The purpose of this virtual revolute joint is to make our life easier. So what I'm going to do is I'm going to draw the new kinematic diagram with this virtual revolute joint. And then you will realize what happens. So this becomes my first revolute joint. Then I have a second revolute joint. This revolute joint did not exist in the initial robot, but this virtual joint I added just to make my life easier. And this is a virtual revolute joint. So what I'm gonna do is I'm going to add my next revolute joint to this virtual revolute joint. So since I added this virtual revolute joint, nobody has prevented me from making the outer limb of the robot or the end effector of the robot perpendicular to the previous degree of freedom. So now I have a revolute joint, I have a virtual revolute joint, I have a final revolute joint, and I have an end effector. So what I'm going to do is I am going to add exactly the same way z naught, x naught, y naught. And I'm going to add the coordinate system on same thing. I will add a virtual, so I would add something like so I need to draw properly. So this is x naught. I will have z1, and my x1 has to be perpendicular to the old and the new z1s. So I will have my x1 like this, my z1, and then I have x1. So my y1 is going to be like this. So I have x1, I have z1. Then I will have to add my z2s. So I have z2, and then my x's, they have to be x2 has to be perpendicular to the z2s and z1. So I would have this guy over here, which would be my x2, and then what I would have y1 in other direction. Okay, let me see. Z1, yeah, correct. Y1 will be in opposite direction. Correct. Y1 will be like this. Y1 will be like this. I have Z2, then I have X2, and then I have Y2 like this. And last but not least, I have X3, I have Z3, and I have Y3. Okay, before I proceed any further, everyone understood what we did? We added a virtual joint, VR, that allowed us to make the R, this revolute joint and end effector perpendicular. Now what I'm going to do is, please note, first I'm going to find out 0 R1. When I find out 0 R1, this is theta 1. I'm going to add theta 2 here. Then I'm going to add theta 3 over here. So it will become cosine theta 1 minus sine theta 1, sine theta 1, cosine theta 1, 0, 0, 0, 0, 1. Here, now please note, I will treat virtual joint as any other joint, which means I'm going to have x1, y1, z1. I would have x0, y0, z0. So let's see, x1 is in the direction of y1. Y1 is in the direction of z0. And z1 is in the direction of x0. So when I perform this multiplication, what I have is I have the complete homogeneous transformation matrix, or 0 R1. So let me write down what 0 R1 is going to look like in this case. First row, first column, that gives me minus sine theta 1. First row, second column, that gives me 0. First row, third column gives me cosine of theta 1. Second row, first column, that gives me cosine theta 1. Second row, second column gives me 0. Second row, third column, that gives me sine theta 1. I have 0, 1, 0. Everybody understood what I have done here? Now, here is the next question. And that question is, how do I go from this virtual joint to the next joint? And the idea is same, 1R2. To find 1R2, I'm going to have, once again, check this out. I'm going to have cosine theta 2 minus sine theta 2, sine theta 2, cosine theta 2, 0, 0, 0, 0, 1. Next thing, what I need to do is, and I want you everyone to please pay close attention. I have x2, y2, z2. I have x1, y1, z1. Let's look at x2. X2, when I look at x2 is in the direction of y1, 0, 0. When I look at y2 is in the direction of z1, and I have z2 that is in the direction of x1. So I'm going to use some space over here. So I have 1 R2 is equal to first row first column minus sine theta 2, first row second column, that is 0, first row third column cosine theta 2, first row first column cosine theta 2, first row second column 0, first row third column sine theta 2, 0, 1, 0. Okay, everyone understood what I have done? Now let me finish the discussion, and let me do this just a second, and you hold your question for a second, please. Now please note, in my original equation, I'm gonna rewrite this is my coordinate frame, z0, y0, x0, and because of this virtual joint, I got additional value of theta in between. So the way I'm gonna rewrite this whole thing, ideally I wanna go from this joint, which is joint number 0 or joint number R0, frame 0, all the way to this frame, which is frame 2. So frame 2. And the transformation is 0 R2. Or I'm interested in finding either 0 or 2. So 0 R2 now can be written as 0 R1 multiplied by 1 R2. The transformation can now be written as 0 R1, 1 R2. Now please note, I already have 0 R1. 0 R1 is minus sine theta 1, 0, cosine theta 1, cosine theta 1, 0, sine theta 1, 0, 1, 0. However, if you look at the way the problem is set up, theta 2, basically theta 2 is actually a constant, and that angle is say 30 degrees. So theta 2 is 30 degrees. And I want you to note that this 30 degrees, this theta is 30 degrees. This is positive. Look at the convention of the way we have defined the joint. So what I'm going to do is, here I'm going to write minus sine 30, 0, cosine 30, cosine 30, 0, sine 30, 0, 1, 0. And with this, I have 0 R2. And then the solution can proceed further. So what I want you to look at is we added a virtual joint, but this virtual joint, we assume that can change angles theta. But if you look at the geometry, this virtual joint is fixed and that angle is 30 degrees. So I substituted that angle in the projection in the second matrix, which is 1 R2 that we got from here. And then I actually took care of the inclined link. So inside MATLAB, when you are trying to solve, you can actually solve the problem the way is set up over here. You can solve the problem the way is set up over here. But instead of theta 2 as variable, just substitute theta 2 as 30 degrees and you would get the correct answer. So that is how you will solve an inclined link problem. And I'm gonna stop here, but I'm stop recording, but I will be happy to answer any questions you may have.